All right, guys, so in this next video, we're going to be looking at diffraction, okay? Now, in the first one, we looked at reflection, which is the waves bouncing off of a surface. We also looked at refraction, which is the bending of the waves due to a change in speed as it goes from one medium to another, or as the medium changes, as we found out with the water. As the depth changed, it caused the wave to change slightly. So when the medium is changing, either its properties or what it is, that's when we get refraction. Diffraction will happen when the medium is consistent, but when the wave passes a boundary, when it passes some type of corner or a slit. A slit basically is just two corners together. We saw this in the video, right? You saw what was happening as we looked at the video and the waves passing through, is that we got the wave going this way, right? These are my rays, remember? And then we've got the blue, which is the wave fronts, marking the crest. And as it approached this slit, what happened? Well, we saw, as I have in the picture over here, that the waves didn't just go straight through like this, that the waves actually spread out, as in they spread out further and further. All right, so that's one of the things that we want to kind of pay attention to as we look at diffraction. Notice that this is basically one corner that it's bending around this way, and a second corner that's bending around that way. So as long as there's a corner, some type of obstruction there, it is going to bend around that corner. All right, we'll talk about why this happens and some other things shortly. All right. So, next. So, next we're looking at just this idea of diffraction. One of the things that we recognized in the video is that the bigger the space, the bigger the slit, the bigger the aperture, the less diffraction it seemed was taking place, right? Here we had a very small slit, and you can see how the spread is doubling, is tripling, right? It's spreading out significantly. Even though the actual angle of spread is more or less the same, this one doesn't look like it's spreading very much, right? It actually looks fairly flat, okay? And as it gets bigger, it's even less noticeable. One of the things that you need to know about diffraction is that diffraction is significant when the wavelength is approximately equal to the width of the slit. Okay, and so when the wavelength is about equal to the slit, then that's when you're going to see significant amounts of diffraction happening. Okay, as I mentioned in the first video, we also are going to see this idea of bending around a single corner. It doesn't have to be a whole slit. Or it actually works if you have a full obstacle in the middle and it's going to bend around the edges. And actually when these waves meet, we're going to get something completely different and actually quite interesting when we do that. But we'll worry about that a little bit later. Okay. Notice that as time passes, as it goes through, what do you think is going to happen to the amplitude of these waves? Well, hopefully you said that the amplitude is going to go down, right? Because the energy that's being carried by this wave is no longer just being carried over this area, it's being stretched out, which means that the energy, in addition to the wave being spread out, that means that the energy itself is being spread out, okay? Notice that the frequency is not changing, the wavelength is not changing, but the amount of energy is going to decrease as we spread out more and more and more, because the amplitude of the wave is decreasing because it's being spread out over this area. Now, that then means that energy and amplitude have some type of relationship, which we'll talk about here shortly. All right. Next, we've got an idea. This is the theory, I guess, a principle behind why this is happening. Okay. So Huygen's principle basically says if you take any wave and choose points on that wave, that the wave will spread out from that point. Okay, so let's look at this one right here first. Okay, the one over on the right. I want you to see. So we're choosing some points right here. Okay, Now the wave is going to spread out from those points. Here the wave is moving this direction. This is one issue with Huygen's principle, is it actually doesn't work in both directions. Why isn't the wave spreading out in both directions? That's a problem. All models have some type of problem because the model is trying to simplify things, and so in simplifying we're going to lose some things. Okay, but this principle, we're looking forward. If the wave were to spread out like this, right, each one of those would spread out exactly the same amount, okay, multiplying the speed of the wave times the amount of time that it's traveling, okay, you'll notice that each one of those crests will be in exactly the same place. Now, in some places, you've got a little bit of superposition going on, right, because you have from each of those points, you have where the wave should be. You add those together, it's going to give you this point. Add those together, it's going to give you this point. Add those together. So what we get is a single wave. So Huygen's principle works for a wave that's just moving along, right? We can see it in a wave that is emanating from a single source or from a wave that's diffracting as well, right? If we look on a curved wavefront like this, and we create those wavelets, we can call them wavelets, is usually what we call them, secondary wavelets. So we create those wavelets. What happens? Well, here's the edges, okay, and then the places where they add together right here, right, that'll add together to give me this will add together to give me that, and so the waves do add up to be along the new wavefront surface. That's where the wavefront will be after a certain amount of time, okay? Let's look at specifically a situation of diffraction over here, okay? So when we're looking at the diffraction here, we have the wave that's coming in, it's moving, there's our ray, it's moving that way. So the wave fronts are moving towards the slit. It gets here, okay, let's take some of these points right here, okay? What would it look like? Well, here, you look at this level right here, okay? I'm going to copy it in purple so it looks a little bit better. What do you see there, right? So over here, it's going to be kind of curved like that, and then where it's overlapping, it should just kind of go on a straight line like this, right? And so that's where there's our nice purple line right there, okay? Now what's going to happen a couple of seconds later? Let's do another color here. So that circle, which was here, is now spread out a little bit further, right? So this red is around this one right here. This one right here is around that one, right? This one, I'm trying to make this clear by using the different colors for you, and hopefully this is working. Let's see, we got that one for this guy right here, we've got that one for this guy right here, and we've got this one for that guy right there. So taking all of those waves and adding them together, notice that we've got this wave over here that's the only one out there, and it comes over here, and we've got some waves being added together in a couple of these positions, and so it should go something like this. Okay, so there's the next one. All right, now I'm going to skip ahead a couple more just because I don't want to go through every single one here. Okay, but we'll go yellow now. So if I skip ahead, let's skip ahead to like this one right here, right? So there is for this one. Let's see, there, no, not that one, there's this one right here, okay, right there, okay, I think you'll be able to get the idea, not that one, this one right here, okay, I'm not drawing in all of them, but hopefully this will be enough to give you an idea of what we're looking at. Right? Again, you can see how on the edges it's just a single wave. We're adding those waves together and we add up to get some type of wave like this. And so you can see how using Huygen's principle, it makes sense that if each point emanates out in all directions, if every single point emanates out in all directions, then we would get this kind of diffraction, this spreading out, and that allows us to figure out what that spreading out would look like. Okay? So that's Huygen's principle. It's an idea that you should know. I think that's good. Let's move on. All right, let's practice. Do a problem. Okay, at a distance of 15 meters from the source, the intensity of a loud sound is 2 times 10 to the negative fourth watts per meter squared. Show that the intensity at 120 meters from the source is approximately 3 times 10 to the negative 6 watts per meter squared, and deduce how the amplitude of the wave changes. So this is actually going to use an equation from our formula packet, okay? The equation is I equals P over 4 pi r squared, okay? If I encourage you to take a second to pause the video and go and find this equation so that you know where it is, okay? This is an important equation because it relates intensity to power and distance. Okay? So intensity is how bright or how much energy per area there is at the point where we're observing. So this is the observer. At the observer, okay? The power is the power that's being produced at the source. Okay, now the idea behind why this works is because you have, now remember we're talking about something here that is producing some type of wave, right? And we're looking at Huygen's principle, which then spreads out from that point, right, in a circle like this, and it spreads out and spreads out, right? Sorry, my wavelength should be more or less the same, but it's spreading out, okay? Now, the important thing to recognize is that as it spreads out, right, it's spreading out in multiple directions, right? It's spreading out over an area, right? This is actually concentric spheres, right? No matter whether you look at it this way or that way, but the idea is as we get further away, all of that power is being spread out, okay? So it's not a linear relationship, it's a quadratic relationship because that energy is being spread out over a width, but also over, it's kind of coming out of the page and into the page, right? And so any power that's being produced by a wave, whether it be a sound or light from a star or whatever it is, it's spreading out in all dimensions, right? As it moves forward, it's moving left and right, but it's also moving up and down. We can't restrict it to just that left-right plane, okay? So because of that, what's the area of a sphere? Okay, if you imagine that these are big old spheres, okay, well, the area of a sphere is 4 pi r squared. So whatever power was being produced here is now spread out over that whole sphere, okay? So the power divided by the area of the sphere over which it's spread out is now the intensity at a point on that sphere, okay? We move out a little bit further as the energy spreads out a little bit more. And how much energy is going to be at a specific area on that surface? Well, it's going to depend on how big that sphere is because now all the energy is spread out over that sphere and so on and so forth. We get out a little bit further. How much energy is going to be in that area right there? Well, it depends on how far out we've moved and how big this sphere is because all of the energy that was there is now spread out over this whole sphere. All right, so that's the idea behind why this equation works, okay? So, because we know that the power is going to be the same in both situations, right, then what we can do is we can say, well, if the power is the same regardless of our distance, okay, then we can take our equation and rearrange it so that it's P equals I times 4 pi r squared. And the power is going to be the same, so that means that this initially, or at 15 meters, needs to be equal to the same thing, I times 4 pi r squared, at 120 meters. All right? And so we're going to go ahead and just solve that, just like that. So we'll say, all right, the intensity at 15 meters was 2 times 10 to the negative fourth watts per meter squared. That is going to be multiplied by 4 pi r squared, so 15 squared, equals the intensity at this point we're trying to show that the intensity is this. So we should be able to solve for intensity. Anytime it says show that, okay, we can't use this number, okay? We have to show that that's the correct number. So this is a command term that they use often in physics and math as well, is that when we're showing something, we can't use that result. We have to actually prove that that result is the correct one. So intensity times 4 pi times r squared. Okay, notice that the distance was in meters. When I square the meters here and the divide by meters squared there is going to cancel out, leaving me power, showing that the power on this side is equal to the power on that side. You should also be able to recognize that the 4 pi is the same on both sides, so you can take that out. Okay, now when we actually work that out, you should end up getting that the intensity, and I'll let you work it out on your calculator. Please make sure that you can get intensity equals 3.1 times 10 to the negative 6 watts per meter squared, because it's intensity. That should be the correct units. Now, when you're doing this, you do need to write this down. You cannot just say, oh yeah, that's 3 times 10 to the negative 6. Okay? You have to write down at least one extra decimal place. Okay? One extra sig fig to show that the answer that you got is actually going to round to give you the show that they gave you. So this question has two purposes. One is to teach you the equation, I equals P over 4 pi r squared. The other is to talk about this show that in case we haven't had a chance to really develop that idea yet. Okay, so make sure you don't use the 3 times 10 to the negative 6. Make sure when you get the answer you write down at least one more significant figure. And there we go. So the intensity is less. So if the intensity is less, what does that mean about the amplitude? Well, the amplitude, remember, is related to the energy, right? So if the amplitude has gone down significantly, right, from 2 times 10 to the negative 4th down to 3.1 times 10 to the negative 6, that's almost 100 times smaller than it used to be. Well, this is something that a relationship that will be worth knowing, and I'm actually going to go through this on the next page. So let's go ahead and go to that. There are a couple of relationships that you need to know. Okay, one is the amplitude one, which I was hoping that we would get on the previous slide, but we'll go ahead and talk about it now. Energy is proportional to amplitude squared. Okay, so if the amplitude doubles, so what this is, energy, remember power is energy over time, so all these relationships for energy will also relate to power and will also relate to intensity, because intensity is power over area. Remember, power equals energy over time. So if energy doubles, power doubles, as long as time stays the same. Okay, and remember that intensity equals power over area. So if power doubles, intensity will double, as long as the area stays the same, right? So these things, energy, power, intensity, are all interrelated. You need to recognize that they are close. They're not the same thing, but they are very closely related. And as long as the other things stay the same, as one goes up, the other will go up. Okay, so one of the things is that energy needs to be proportional to amplitude squared. Okay, and we've done a little bit of this before. In math, we're talking about direct variation right now. So what this is that energy has a direct variation relationship with amplitude squared. Okay, or in other words, if I double the amplitude, so I go 2a, that would give me, if I distribute the a, it would be, if I distribute the squared, that would give me 4a squared, which means that the energy is now 4 times what it used to be. Okay, so doubling the amplitude is going to quadruple the energy there. Okay, another relationship is that you should recognize that energy is proportional to frequency. Now this you should already know. We've talked a little bit about waves and frequencies and things like that, but you know that X-rays are much more dangerous than visible light, right? You don't walk outside nervous that your hair is going to fall out, because visible light is much lower energy, right? You don't worry about walking out, you don't worry about being sunburned inside the house, even though the light bulbs are on. That's because the ultraviolet light coming from the sun outside is much higher energy than the visible light coming from your light bulbs. Okay, the visible light from the sun is not what burns you. It's the ultraviolet light, the higher energy light that's there. Okay. This also goes into our cell phones dangerous, or the that type of thing. The waves being sent off. Those waves are so low energy, right? They're so low energy that they're not going to hurt you. That's like saying you should turn off all the lights in your house and don't go outside during the daytime because the light waves are going to be harmful. Ridiculous, right? So kind of think about that when people start talking about, oh, it's so dangerous, the waves and the microwaves. Yeah. Think about your Armivux, right? Armivux, right? Here's visible light, here's heat, infrared, and then here's microwaves. Microwaves have such low energy, they're much less worrisome than visible light. So anyway, so remember these things. Energy is proportional to frequency. Energy is proportional to amplitude squared. And then remember that intensity has this link, right? There's this link for intensity because intensity is power over area. Power equals energy over time. So as long as time, area, those things are staying the same, if you double energy, you're going to double power. If you double power, you're going to double intensity. All those things are then connected. All right? So that's it for this video, and hopefully that gives you a little bit better idea of what's happening during this diffraction, the spreading out of waves.